Hello, and thanks for checking out Eco Simulator, my artificial life simulation program. You may have seen an earlier video that I released about this program, but there's been a lot of updates and there's a lot of new features, so I'd encourage you to stick around and see all the new content that I've added. Otherwise, if you're new to this program, this video should be a nice overview of what it is and what you can accomplish with it. So with that, let's get started. So I mentioned that my program is an artificial life simulation. And I know that some of you may not be very familiar with the field of artificial life. So I just wanted to give you a quick introduction to the field so that you have some background and maybe a better understanding of my motivations and what I'd like to accomplish with this project. So I'll start with this quote. Artificial life attempts to understand the essential general properties of living systems by synthesizing lifelike behavior in software, hardware, and biochemicals. So I think a common approach in this field is to try to create systems from the ground up to share many basic characteristics with life, and then to see what kinds of properties or patterns emerge from those systems. And this is opposed to using more of a top-down approach where you're trying to fit a mathematical model to a system that already exists. In some ways, this field is similar to the field of AI, especially with the recent focus on neural networks and evolutionary algorithms in AI. But whereas AI tends to use these biologically inspired systems to understand the emergence of intelligence, artificial life is using these sorts of systems to better understand life and its properties and the characteristics of living systems. For example, you might be interested in learning how cooperation or competition can emerge, or maybe how multicellular life might emerge from single-celled organisms. So in terms of my program, I've tried to create this really open-ended and customizable tool for studying various different topics in the field of artificial life. In particular, I think it would be useful for studying different aspects of evolution, how creatures evolve in a complex system. It could also be useful for studying how stable a system is. Is it about to collapse? What factors influence that stability or instability? And finally, I think it could be really interesting to look at if cooperative or competitive behaviors could come out of a system like this. So before we go over to the demo, I just want to give you a quick overview of the system and some of the main components that make it work. So it's an agent-based system where each agent is analogous to a creature or some kind of an organism. Each agent has its own set of neural networks that guides its behavior. The user starts by creating populations of agents, which will then evolve over time through a process that's similar to natural selection. So this is where some of the agents are dying out while others are surviving and reproducing and passing on their genetic material. So in this case, the weights of that agent's neural network serve as their genetic material because that's what's guiding their behavior. Yeah, so I think that should be some good background for the demo. So let's head over to that next. So I'm developing this program in the Unity game engine, so I'll just start it up from there. And I'll just start with a really simple simulation where it's pretty easy to see what's going on. So each of these blue specks is a creature, and as you can see they're moving around through their two-dimensional environment. And then the gray background is representing how much resource is available in a particular location. So the brighter the square, the more resources there. And in this case, I've distributed the resources from less at the bottom to more at the top, just for the sake of experiment, but you can distribute them in other ways as well. And you can see some of the creatures are leaving this sort of trail of depleted resources behind them as they consume from these land squares. I actually do have one other resource on this map, which I'm kind of using to limit their reproduction, so they don't, their population size doesn't really explode and become too big. which doesn't seem like it's happening at this point. But yeah, so I also wanted to go over a few ways in which you can control the simulation. So you can pause it, unpause it, speed up the refresh rate, which will work as long as there's future ecosystem states to render. You can also change the number of simulation steps between each rendering. So if I set this to 20, it definitely speeds up the rate at which you're seeing things happen. You can even go higher than that if you want. So you can kind of watch the progress of things at different time scales. So I also wanted to cover a few details about the creatures. You can actually click on the creature and view some of its statistics. So this first window shows some of the basic info for our creature. It tells us the species, the ID, which is a little complicated. This first number is the index of one of the original creatures in the original population. So it's the 17th creature that was created in that first population. And then the subsequent numbers represent the creature's lineage, and it starts at 0. This is actually the second child of the fourth child of the third of creature 17. So you can kind of see who's descended from who. It has the health of the creature, which if it hits 0, then the creature dies. Shows the mutation amount, which is basically how different the children will be from the parent. You can also view the resources that are stored in the creature. And so these resources, you can set various parameters about if a resource drops below a certain level, it could have a negative health impact, or if it gets above a certain level, it could give them a health boost. Different actions have different resource requirements, so like I've made it so that the creatures need a certain amount of this vitamin resource in order to reproduce. So a lot of that can be customized. So you can also look at the creature's neural networks. So in this example, there's basically 2 layers of networks. These input networks that are associated with getting inputs from the environment or the creature's internal state. And then we have these output networks, each of which is associated with a different action, like moving up, moving down, eating, reproducing. So let's take a look inside one of these. So yeah, as you can see, the user interface does need a little bit of work still, but these are network layers. We have our input layer, a hidden layer, and an output layer. You can definitely customize the number of hidden layers and the number of nodes per layer. You can customize what inputs you'd like and what actions you'd want to associate that network with. It looks like this is associated with sensing the level of grass on surrounding squares and the vitamin resource as well. And so these are like basically the fractions of the amount of that resource on those squares. And then this output layer is basically assigning information to be sent to one of these output networks. So if we look at, like, say, eat vitamin, this number is being sent over to this network, and it's one of the nodes in the input layer of this network. So it basically gets inputs from different networks, combines those to make a final decision about whether or not the creature should eat a vitamin, or try to attempt to eat that resource on the square it's on. This number is the probability that it will attempt to perform that action, or that that's actually the probability associated with the turn that just occurred. And that doesn't necessarily mean that it was able to perform that. If it attempts it, it might not have enough resources to actually perform it, and in that case, there isn't really any penalty for the creature. But of course, if it is able to do it, then there are resource costs, and so there are consequences if it is able to perform it. One other sort of detail is, I think I said in this case, I set it so that each action basically takes the entire turn to perform. But you can make it so that different actions take a certain amount of time that's less than the turn time, so they can do multiple things in each turn. So that's all customizable as well. Yeah, so that's a overview of some of the main characteristics of the creatures. And next I'd like to do a few sort of experiments related to genetic variability and mutation and that sort of thing. Alright, to set things up, I'm going to start by increasing our map size to 200 by 200, just to make things a little more interesting. And then I'm going to set our creature's mutation rate to 0, and the initial population variability to 0. So this way we'll be just creating a population of essentially just all the same individual, a bunch of clones. And I think that'll be an interesting place to start. Alright, so let's start up this system. So as you can see, despite all the creatures being identical in terms of their weights, they're still exhibiting a little bit different behaviors, and this is just because their actions are determined probabilistically, and so there's an element of chance there, and they may be getting slightly different inputs to their neural networks as well. But it looks like for a few of them there's kind of a trend to move upwards a few steps. That might be something that's kind of encoded into those genes. It looks like a lot of them haven't eaten enough to continue moving, so they're pretty quickly dying out here. And so, yeah, that kind of random guess at a set of weights wasn't necessarily a very good one for survival. And without a mutation rate, they didn't really have any capacity to adapt. So it looks like that population only lasted a little over 100 steps. And it could be that they just didn't know to eat enough, or maybe they weren't moving quickly enough, something along those lines. Maybe they should have been reproducing. But yeah, whatever the case, they just didn't happen to have very good genes. So next I want to look into a couple different techniques for creating creatures that are better adapted to this environment. Alright, so back in the code, I'm just going to make one simple change, adding some population variability, making it so that each individual in that original population is a little bit different from one another. And we'll see what effect that has. So let's start up this one. And in this case, I'd expect to see some fairly different behaviors from each of these individual creatures in our initial population. So let's see if we can see any patterns. Yeah, so it looks like this one's moving pretty strongly up, whereas some of them are moving a little more to the left or more to the right. So there's a little variation there. Oh, and these are moving like basically straight down, so that's actually fairly different from the others. Some of them are surviving, much longer than others, so there's some variability there. And but overall, this system seems to be maintaining itself for quite a bit longer than the one we just looked at. I think because you're basically making 100 different guesses at a good set of weights rather than just one. So let's speed this up a little bit more and see how long it lasts. This creature is doing pretty well, but it seems like a lot of these creatures are just going to run up against a wall and then basically die out. So, okay. There's a couple left. I could probably show you these. I would guess are descended from one of the original creatures, whereas these, with a different behavior, are descended from a different one. So that kind of goes along with our line of thinking. So let's see. This one lasted about a little over 2,000 steps, so much better than the last system, but evidently not able to maintain itself for an extended period still. So let's try changing one other variable here. So this time I'm going to leave the population variability the same, but I'm going to give the creatures the capacity to mutate a little bit each time they reproduce. So we'll see how that affects the system. Alright, so let's start up this one. So initially the system might look fairly similar to the last one, but over time I'm hoping to see a few kind of long-term differences. So yeah, initially they're moving in different directions, but even as they reproduce, their offspring might even choose a different direction to move. So that's one difference. And basically what this is doing is each time they're reproducing, they're introducing new genetic material into the system, into the population. And so the amount of overall variability for the population tends to increase over time with this technique. And yeah, I have some basic numbers here. Yeah, this user interface still needs a little work, but this is the population size for the creature and the amount of genetic variability, which is actually quite high right now, and it might even be going up still. So while this seems to be a fairly successful system, you know, apparently it's a fairly good strategy to be mutating quite a bit each time and exploring more and more of this fitness landscape of all the possible sort of sets of weights that you can choose. That genetic variability does kind of have some downsides in terms of if our goal was to just create one creature that has an ideal set of weights and we want to know what those weights are, it's pretty difficult to choose that set of weights when there's so much variability in our population. So it's interesting to see that this seems to be a successful strategy. And I should mention, if you set the mutation too high, it's actually not so successful because their behaviors become too extreme. But next I want to talk about a way that we can explore this fitness landscape initially, you know, quite a bit, but then sort of settle into some local optima after a while and have a better chance of pinpointing one set of weights that we think is well adapted. So it's kind of a process that's similar to simulated annealing in some ways. But yeah, in that case, we'll be reducing the mutation rate over time. So let's go to that next. So back in the code, I just want to set a few parameters here. This parameter is actually the lowest possible level of mutation. So I'm going to set that to 0.01. This is the initial amount of mutation, which last time that was just a constant. But this time I'm going to change this key parameter, which is what you multiply the mutation rate by each time the creature reproduces. So if I set this to 0.9, when that creature reproduces, its mutation rate's going to go from 1 down to 0.9. If it reproduces again, it's going to get even smaller, and it will be passing on those lower mutation rates to its children as well. So over time, as the mutation rate goes down, the population won't be adding quite as much new variability to the system. So let's try that out. Alright, so back in Unity, I've started our new system. I'm going to set a high number of steps for each interval to watch things progress a little more quickly. It can take a little while for this reduced mutation rate to really take effect. But yeah, one sort of key statistic for looking at how effective that is this measure of overall population variability. So you might be wondering where that number is coming from. And if I can click on one of these creatures, go back to its weights, I mentioned each creature has its own set of weights, but you can also take the average for each weight across the whole population and look at the standard deviation for that weight across the population. So as you can imagine, this might be useful if you're trying to hone in on one particular set of weights that you can use to create a well-adapted creature. And so that number that I mentioned at the bottom, that comes from taking the average of all the standard deviations. I think I actually take the average variance and then the square root, but fairly similar measurement there. So the idea is if that amount of standard deviation for all the weights is dropping down enough, which it looks like it's dropped down a little bit, then we may have happened upon a set of weights that seems to be fairly stable, and if the creatures are surviving in the system, then it's well adapted, or it's an adaptive set of weights. So I usually like to let the system run for a little while and let it find that set of weights that seems to be really ideal for surviving in this environment. I should probably mention there's a couple sort of caveats to just taking those averages. There could be several subpopulations across this environment where some of them have one set of weights that seems to work in one way, and some other ones have a different set of weights that works in a different way. And just taking the average of those two might be taking you off of the local optima to somewhere in between two optima. But that said, it could still be a better set of weights than, much better than just a random guess, which is what I'd like to kind of go to in the next example, is looking at what happens when we just take the average of these sets of weights that we've come up with. So I think I'll let this run a little bit longer. A lot of times I like to go somewhere between 5,000 and 10,000 steps. As the levels of resources are going down, that actually can sometimes create a more challenging environment for the creatures to survive in. So it kind of forces that hill climbing towards optima a little bit more. But yeah, I'll run it for a little while and then just come back to you in a minute. Okay, so here we are at a little over 10,000 steps, so I've given the creatures quite a while to adapt. I'm not sure if I mentioned the resources are renewing in this case, so it's not like they'll consume all the resources and die out, but there are maybe less resources than in the beginning of the simulation. But yeah, the genetic variabilities drop down below 1, which is not too bad. I think it could be worth taking the averages at this point and looking at what we come up with. Alright, so this time I want to actually use the averages from the last population that we just ran to create our new population. So in order to do that, I'm going to set this parameter to true, which basically says take those averages that were saved to a file, load them, and use them for this new population. And eventually I'd like to create a better saving and loading system, but this is just kind of an early implementation prototype. And then just to kind of reduce the influence of any other factors on this system, I'm going to set the mutation rate to 0, as well as the initial population variability to 0. So we basically just have, again, a bunch of clones of the same individual, but hopefully in this case, those individuals will be a little bit better adapted. So let's go find out. Alright, so let's see how our more highly evolved creature does in our initial environment. So as you might remember, the last time we tried to create a population with all identical creatures, it didn't really do very well. It only had I think the whole population died out after a little over 100 steps, and it might be surprising for it to last more than a couple thousand steps, just randomly guessing weights. But using these weights that we've evolved over thousands of steps, you can already see that this population seems to be doing quite a bit better. It does maybe have a slight tendency to move to the right, which might not be very adaptive, and that sort of thing could happen when you have a totally uniform population like this with no variability or mutation rate. But that said, they're proliferating and surviving. They have a pretty large population size at this point, where it's even maybe slowing down the simulation a little bit. It's gotten so big. And just to show you that the neural network weights really are all the same, you can see that the value is equal to the average with no deviation. Yeah, so we could watch this progress for just a little while, see the end product of all of our attempts at evolving this ideal creature. And then, you know, of course, if you were to allow this creature to mutate a little bit, it would probably be even more effective than it is now, even with, you know, a small amount of mutation. Yeah, and they're also, you know, maybe consuming more of the resources than they should be. And that could be because they've adapted to survive in a different kind of environment, and maybe the kind of cues that they're receiving for performing actions were a little bit different in that environment than in this particular one that they've been put back into. But, yeah, I made it over 1,000. Maybe I'll just come back once I see that this creature is on the decline, and that way I can let you know how long it survives. So several thousand steps later, it looks like our creature is finally on the decline, about to go extinct here. But that said, you know, it made it several thousand steps rather than just a few hundred, as seemed to be the case with when we're just randomly choosing a set of weights. So yeah, it seems like evolving these weights did have a pretty large impact on how long the population could survive. Yeah, and so in the future, I might want to do an actual statistical analysis and try to quantify that. But yeah, hopefully this sort of series of demos has given you a better idea of these different factors that can influence population, like the mutation rate and the variability, so on and so forth. And I just want to get around to one other demo, and this other demo is actually quite a bit different. It'll actually kind of show off more of the features and all the different ways you can customize your creatures and create multiple populations and so on and so forth. Thus far, we've just been kind of dealing with this one basic population of creatures. So yeah, it'll be interesting to get into all the kind of neat customizations you can do. So let's head over to that next. Alright, so back in the Unity editor, now that I've stopped the simulation, I can switch demos by going over in the hierarchy to demos, clicking on simulation test runner. Under thread manager, you can set the demo index. I was just doing demo 1, and I'm going to switch over to demo 2. Alright, so going back to my code, we've been working with this eco demo 1 class, which, if you're looking for a place to investigate how to create an ecosystem with resources, how to put those resources on the map, how to create a creature and add actions and build up its network. This is a fairly simple example, and just walking through the code, I think you could learn quite a bit about how the program works and how you could create your own ecosystem if you wanted to. But now we're going to switch over to the Eco Demo 2 class. I just have 2 of these demo classes at the moment. But yeah, feel free to create your own and experiment around with changing parameters in these and seeing what kind of systems and populations you can create. So Eco Demo 2 is a little more complicated. We're adding 2 different species to our map, and they have this kind of complex resource dependency between them. So I'm just going to start up the simulation and kind of explain it from there. Alright, so as you can see in this system, I've created populations for 2 different species, one that's represented with blue and another one that's green. And as you can see, the resources have also been distributed differently, where I've just randomly created overlapping clusters across the map. And so I've used that pattern for resources A and B, which are the primary resources for these two populations. It looks like green is eating B and blue is consuming A. But then these other two resources are a little more interesting. I created a sort of baseline amount of the resource on the map, but they don't actually renew. The source of those resources is actually from the creatures themselves. So in terms of resource C, it looks like green is producing it while blue is consuming it. And then the opposite is true for resource D, where it looks like green is consuming it and blue is producing it. So there's this kind of interdependency of the two species on each other in terms of producing the resources they need. And you can see that if you go into their neural networks. Let's see, this was, I think, creature 1 is the blue creatures. They're consuming A. C is the resource that green is producing that they need, so they're eating that. But they're also converting A to D, which is what green needs, and depositing that resource for green to pick up and consume. So, it could be interesting to see if, run over enough time, maybe these two species will learn to cooperate and produce a certain amount of the resource that the other creature needs, even though they pay a slight cost in terms of time and their own resources. If one dies out, then the other one also dies out. So, I think it'd be interesting to see if they can learn to cooperate. And this is just one example of all the different sort of scenarios and experiments you can create with this program by designing your own species and populating them across the map. So hopefully that gives you a good idea of some of the things you can do with this program. Hopefully it captured a little bit of your interest. The program's up on GitHub. It has a couple license options as a GPL license and another license you can use for commercial purposes. So I encourage you to look into the code and hopefully experiment around with this a little bit, have fun with it, and thanks for watching.